All right, so let's get started. So in the previous class, we were discussing about MOSFET, so metal oxide semiconductor-based field effect transistors, and we saw that the MOSFET have very particular current versus voltage characteristic. So if you plot the VDS on the x-axis and the current through the MOSFET on the y-axis, you will see that initially the current increases with your voltage. That's what you expect from any traditional resistor as well, that the current across or current through a resistance will be proportional to the voltage across it, right? That's Ohm's law. Now, for the MOSFET, when your voltage across the MOSFET is small, you'll see that the current through the MOSFET is proportional to the voltage across it, just like a resistance. And that is the region which is called the linear region of the MOSFET behavior. But then there will be a region when you'll see that the ID versus VDS characteristic of the MOSFET will saturate. So if we look into this plot, initially, as you are seeing, that as you are increasing the drain to source voltage, that is the voltage across the MOSFET. Remember, if this is your MOSFET, this is the gate terminal, this is the drain terminal, and this is the source terminal. So this is for an N-channel MOSFET. And we'll be discussing everything about an N-channel MOSFET initially, and then later on we'll try to map all the results to a P-channel MOSFET. But if you understand N-channel MOSFET, there will be no trouble understanding the P-channel MOSFET because both are just basically the dual of each other. So if you understand one, the other one does not need much understanding to do effectively. So this is your N-channel MOSFET where the current flows from drain to source. Again, why? Because for an N-channel MOSFET, the charge carriers are the electrons, and electrons or the charge carriers will always flow from the source to the drain. So if the charge carriers or the electrons are flowing from source to drain, the current will flow from drain to source, right? So that's what will happen in an N-channel MOSFET. And the voltage from the drain to source terminal is your VDS. The current flowing from the drain terminal through the source terminal is called ID. So that would be the notation that we'll always use when you're talking about MOSFETs. So ID is the current and VDS is the voltage across the drain to source terminal. Now, this is what I was talking about, that initially when VDS is small, you'll see that the current through the MOSFET will be linearly proportional to the voltage across it, just like a resistance. But as your VDS becomes higher and higher, at some point the current through the MOSFET will saturate. And that's the interesting property of a MOSFET, because this part can be achieved even with a simple resistor. You don't need a MOSFET for that. But this is the part which no other device apart from the MOSFET will provide you. Of course, the BJT can provide you similar things, but BJT is a current controlled current source. The MOSFET is a voltage controlled current source, and it has far more interesting properties than the BJT, as we'll learn later. Okay, so now what we are going to do today first is that in the last lecture, we tried to understand this ID versus VDS characteristics from an intuitive standpoint, what happens when you treat it from the point of view of the energy band diagrams. And this is something we already looked at, that by applying a gate voltage, you're trying to reduce the energy barrier. So remember, we drew something like this in terms of the energy band diagram. This is the N region, this is the P region in the channel, and this is another N. So this could be your source, this could be your drain, and the electrons are trying to flow from source to drain, but in between it sees a wall, it sees a hill. So the electrons cannot flow from source to drain, so you need to do something. What can be that something? You can apply a positive voltage at the gate terminal that will reduce the height of this wall, that will reduce the height of this hill, and it will eventually become something like that. And then you can roll the ball from the source to the drain, or you can roll the electron from the source to the drain, and it will pass through. Now, as you apply a drain voltage, what will happen is that the energy at the drain terminal will also reduce. So this portion in the energy band will also come down. So effectively, you'll start having something like this, right? As you apply more and more drain voltage. So which means as you apply more and more drain voltage, there is a possibility that more and more electrons will roll through from the left side to the right side. And that's what you see in this region, that more and more electrons are flowing from source to drain, so you get more and more current. But after some point, you'll reach a saturation that, okay, even though you are reducing the energy in the drain side more and more, you are limited by how many electrons are there on the left side. How many balls do you have to roll in the source region? And when you are limited by the number of electrons that you have on the source region, effectively you will not, you'll reach a saturation, right? You cannot have more current than the number of electrons that you can pass through. So that's why you have a saturation, and that's what we try to understand intuitively. Today we'll do a much more rigorous mathematical derivation of this. But yeah, then again, we'll eventually use the formula for solving MOSFET-based circuits. Don't worry about the mathematical derivation. The mathematical derivation will not be part of any exam, but if you're interested in circuits, it's a very interesting thing to understand that how mathematically you can show the same thing. And the mathematics we'll be using is again high school level mathematics and physics. So I hope all of you should be able to understand this, but let me just go over that math a little bit more in the first 15 to 20 minutes of today's lecture. All right. So I'll post this document on Canvas. So what you basically have, or what you basically need to go through is this derivation of the IV characteristics. So this is also called IV characteristic or current versus voltage characteristics or ID versus VDS characteristic of the MOSFET. All of those terms will mean the same thing. It's basically the drain current versus the drain to source voltage of the MOSFET. Now, if you consider a semiconductor bar, so let's say this is the bar that I was drawing in the previous lecture, but I did not provide you with this particular document which has all the details. So let's just assume that you have a bar that looks like this. And you want to find out, and this is semiconductor, of course. You want to find out the current through this bar. Okay, let's say that the current is I, and if the charge density along the direction of the current is QD coulombs per meter. Okay, if the charge density is QD coulombs per meter across the direction of the current, and if the velocity of the charge is V meters per second. So what is your current? Your current is basically the amount of charge that is flowing through the bar per second per unit time, right? That is the definition of current. Right? I equal to the total amount of charge that is flowing through it divided by the time, the amount of time that you take to make the charges flow. So if you have a charge density of QD coulombs per meter and velocity is V meters per second, if you multiply the two, what would be the unit? It will be coulomb per second. That is the exact unit of current. Ampere is equal to coulomb per second, right? So if you have the charge density of coulomb per meter, velocity is V meters per second, then current is equal to QD times V. So that's basically, you can also understand it in this way, that the total charge that passes through the cross section of the bar in unit time, now with a velocity of V, all of that charge enclosed in the V meters of that bar must flow through that cross section in unit time or 1 second. So basically, if you have this bar and if the velocity of the charges is V meters per second, so all the charge that is enclosed within V meters of this bar. So this is the bar. You take a cross section and you extend that cross section by V meters. That's the velocity of your charge, velocity of your electrons that are flowing through the bar. So within that cross section multiplied with these V meters, within that entire volume, how much ever charge is present that will move through the bar within 1 second, right? So if that is true, then basically if your charge density is QD, then the total charge in V meters will be QD times V. So the total charge in the volume will be QD times V, because the charge density per unit area was QD, and that entire charge is moving through the bar by V meters within 1 second. So the total amount of charge within V meters that is moving in 1 second is QD times V. So that is also another way you can interpret it. All right. So now the next thing is something we had already discussed in the previous lecture, that what is the value of QD? What is the value of that unit charge, right? Or the charge per unit area? Or, sorry? No, please, go ahead.
It was something like something related with the name.
Right, exactly. So it's basically this equation that you know that charge equal to Q equal to C times V, right? Q equal to the amount of capacitance multiplied the amount of voltage. Now the capacitance per unit area under the channel is COX. and the amount of voltage that you have available at the channel is VGS minus VT. So if this is your channel, so this is your N plus region, let's say this is the source, this side is the drain, and you're applying a gate voltage VG at the gate. The width of the gate is W, the length of the channel is L. Okay, the width of this is W, and the length of the channel is L. So this direction is L. And remember that electrons are flowing along the direction of L. Okay. So if you all agree to that, then basically the amount of charge that you have or the charge density that you have QD will be equal to the amount of capacitance per unit area multiplied with W. Why are we multiplying it with W? Because again, go back to this particular diagram, that this was your bar. The electrons are moving from left to right. The current is flowing from left to right, which means the electrons will move from right to left. That's the opposite direction, but that's fine. What we are trying to say here is that the V meters, the amount by which the charges are advancing or the current is going through within 1 second is from your left to right. But this charge density is taken across this cross section. So if you had a cross section like this in the bar, that's the definition of your charge density, that how much charge is present within this cross section. That is what your QD means. Okay. Now you already have a definition of capacitance per unit area in the channel. So that unit area in the channel, that takes into account the length of the channel and the width of the channel. But if you want to take the charge density for the cross section that we had drawn earlier, you're not taking into consideration the length, the direction along the length, right? You're not taking the direction from left to right, but you are considering the direction from in this way, right? So that's your width. So that's why the total amount of capacitance that you will see is W times COX, and the voltage that you have is basically VGS minus VTH. That's the voltage in the channel. So your QD will be W times COX times VGS minus VT. Now, if your drain voltage is greater than 0, then in the channel, you will not have the same voltage near the source or near. So in the previous case, the channel has the same voltage. It was VGS minus VT, and the same voltage was available at this point, this point, this point, as well as this point. Because you did not apply any voltage at the drain. So all you applied was a voltage at the gate. So just below the gate, you had a voltage drop of VT, which is the threshold voltage of the MOSFET. You need that much threshold to be applied at the gate so that you get a reasonable amount of current flow through it. But the voltage across the channel was constant as a function of your length, as a function of this direction, which you can call the X direction. Okay, so your voltage was constant all throughout. But if you apply a voltage at the drain, then the charge, then the QD in the channel will not remain a constant, will not remain a function which is independent of X. And why is that? Again, this is something we discussed in the last class, that as you apply a voltage, so instead of grounding this drain terminal, if you apply a positive voltage over here, what it will do is that it will attract some of these electrons which are in this channel toward the drain terminal, right? This is a positive charge, and this is a positive voltage applied at the drain, and positive voltage applied at the drain means that you will attract the electrons in the channel toward the drain. So if you have attracted the electrons toward the drain, the electrons cannot be present near the drain, right? They will not be present at this point. And that's what this particular equation means, that you see a gradient in the amount of charge that is present in the channel. Near the source, there will be more number of electrons. Near the drain, there will be less and less number of electrons as you apply your drain voltage. Because the drain voltage, the potential will start attracting the number of electrons from the channel. Right? Positives and negatives attract, right? That's all I am saying here. That if you apply a positive voltage at the drain, it will attract the negatively charged electrons, and you will have less number of electrons near the drain. Okay, so if that is true, then your channel charge density in that case is basically W times COX times this voltage, which will now have this form. It will not only be VGS minus VT, you'll have an additional term of Vx. Now, when x is equal to 0, when you are very close to the source, the Vx is also equal to 0. So near the source, you'll have a voltage of VGS minus VT. But near the drain, you'll have less amount of voltage because you are applying that additional amount of voltage to the drain, and because of that, you'll see a gradient in the amount of charge that is present in the channel, and that's how it can be represented. All right. So now, if we already now know that how to represent the current through the channel, that is QD times the velocity. So you represent current equal to this QD times the velocity, and of course, you will have a negative sign in this case because we are talking about electrons as our charge carriers. Because the current flow is in the opposite direction of the flow of the electrons, you will have this negative sign. But if you had done this derivation for a p-channel MOSFET, it would have had the positive sign, because then the flow of charge carriers will be in the same direction as the flow of the current. But because we are doing it for the n-channel MOSFET, you'll have this negative sign. All right. So now what you are going to do is that you'll represent the velocity as mu times E, where mu is the mobility of charge carriers and E is the electric field. So the velocity of an electron can be represented as mu times E. So that is basically the relation of the velocity of a charge carrier and the field within which you are subjecting it to. And mu is basically a proportionality constant. The velocity is proportional to the electric field, and mu is the proportionality constant, which is called the mobility of the charge carriers. Again, you'll get more details if you take a class on semiconductor device physics. But for this particular class, knowing this much is sufficient, that the velocity of a charge carrier is proportional to the field within which it is subjected to, and the proportionality constant is called mobility. Okay. Now you also know that electric field is equal to minus dV dx. That's the derivative, negative of the derivative of the voltage. So now you can represent this entire current ID as W times COX times VGS minus Vx minus VTH times mu times E, right? And mu E you can represent as dV dx. So that's your entire equation that we have now. So what you can do at this point is that we can integrate this ID current with respect to dx, and you can provide the boundaries of x equal to 0 to x equal to L. Again, why? Because this is your x direction, and at the source, the value of x is equal to 0, and at the drain, the value of x is equal to L. That's the length of the MOSFET, right? So that's why you're integrating it within this boundary from 0 to L. And if you integrate it from 0 to L, on the right-hand side, what you have is V equal to 0 to V equal to VDS. So the voltage is at the source is equal to 0. The voltage at the drain is equal to VDS. So that's the voltage within which you are integrating it. And if you perform this integration, what you will have is basically ID equal to mu n times COX. So this will come outside of the integration because this is not dependent on x. W over L. So W will also come outside of the integration. And L is something you'll get over here on the left-hand side. That you'll get ID multiplied with L because you're integrating from x equal to 0 to x equal to L, and you have integration of dx. So that will become x, and when you put the values of boundary conditions of L and 0, you'll get ID multiplied with L on the left-hand side. So taking that left-hand side L on the right-hand side, it will become, you'll get this W over L term. What is happening to the rest of the equation? So you have a voltage term, and you're integrating it with respect to dV. So of course, you'll get VGS minus VTH times dV, and that's, if you integrate it from V equal to 0 to V equal to VDS, you'll get VGS minus VTH times VDS. The second term is basically this V of x times dV, and if you integrate it from V equal to 0 to V equal to VDS, you will get V squared over 2. So integration of V dV is V squared over 2, right? So integration of V dV is equal to V squared over 2. So we are using that formula for this term, that when you are trying to integrate Vx dV from V equal to 0 to V equal to VDS. And when you put those values, you'll get this minus half VDS squared. So that's your entire equation. And this is the equation we had written down in the previous class as well, that this is your entire equation for your current through the device. Now, let's just assume that now if you just plot it, with respect to your ID versus VDS, what you'll be getting is the equation of these parabolas. This is the equation of a parabola, right? You have a VDS squared term, you have a VDS term, you have your ID. So this becomes an equation of a parabola. Again, going back to your high school math, and the maximum value that will reach will be this point on the parabola, and that maximum point you can find out as half mu n COX W over L times VGS minus VTH whole squared. So how do you find out maxima of a curve? You just take the first derivative and equate it to 0, and then you find out the value at which it reaches that derivative to be equal to 0. Right? That's how we find out the maxima of any curve or any equation. Now, of course, it can be maxima or minima, and for that you generally take a second derivation, and if your second derivation is negative or positive, depending on that, you say whether it's a maxima or minima. But in this case, it's always a maxima, as you see over here, and the maximum value is reached when your the value of your ID max will be half mu n COX times W over L times VGS minus VT whole squared. So this VGS minus VT, as we have mentioned in the previous class, is called the overdrive voltage. That is the amount by which you're applying an additional gate voltage. So you're applying the gate voltage so that you are above the threshold voltage of the MOSFET. The amount by which you are more than the threshold voltage is called the overdrive voltage. That's the amount of overdrive that you have. And as you see that your current is basically proportional, or the maximum current is proportional to the square of the overdrive. That's why the MOSFET is also called a square law device. W over L is the aspect ratio. Now, if your VDS is much smaller than VGS minus VT, if your VDS is very small, your VDS squared will be even smaller. Let's just assume VDS equal to 0.1 volt. What would be VDS squared? VDS squared will be 0.01 volts, right? So 0.1 squared is equal to 0.01. So VDS squared will be even smaller. So you can ignore this term when your VDS is very small. When your VDS is very small, you can ignore this term. If you ignore this term, your ID becomes proportional to VDS. The rest of the things, so for example, mu n COX is a constant, W over L is a constant. Let's say you have applied a constant gate voltage, so your VGS minus VT is also a constant, but your VDS is changing across the x-axis in this plot, right? So your ID is proportional to your VDS. So ID increases as you're increasing your VDS. So this is the equation for the triode region or the linear region of the MOSFET. So this is called the linear region or the triode region for the MOSFET when your VDS is less than equal to VGS minus VT. So that's the definition of your triode region or the linear region, that your VDS has to be less than VGS minus the threshold voltage. All right. So, and this is something we already talked about, that when VDS is much smaller than VGS minus VT, you can represent your ID as a function that is almost proportional to VDS, which means you are in this linear resistive region, and you can also calculate what is the value of that resistance. The value of that resistance is basically your voltage divided by current. So your VDS divided by ID is the value of that resistance. So it is called the on resistance of the MOSFET. Why is it called the on resistance? Because you are applying a gate voltage that is more than the threshold already. That's an assumption. If the applied gate voltage is less than the threshold voltage, then the MOSFET is off. Just like there was a threshold concept of a diode, there is a thresholding concept of a MOSFET. If your gate voltage is small, your MOSFET is off. And you may have heard about this fact that MOSFET can be used as a switch. So in digital logic, MOSFET is usually used as a switch. That means that when your gate voltage is small, gate to source voltage is small for the NMOS, your MOSFET is off, the switch is off. When the gate to source voltage is high enough, the switch turns on, right? So that's just turning on or turning off the MOSFET. In this case, we'll assume that the MOSFET is already on, but your VDS could be less than VGS minus VTH, or it could be more than VGS minus VTH. If it is less than VDS minus VTH, you are in the triode region, and in that triode region, your resistance, the on resistance, is VDS over ID, and VDS over ID is 1 upon mu n CoX, W over L times VGS minus VT. That's your on resistance. Now, of course, for different values of VGS, your curve will look different. If you have a higher VGS, of course, you'll have a higher amount of ID just from this equation. So if your VGS is high, if your VGS increases, your ID will also increase. So that's what we see here, that VGS1 is less than VGS2, less than VGS3. And that's why you have a higher amount of current as you go from VGS1 to VGS2 to VGS3. All right. So next thing we wanted to understand is this saturation region, right? So we now by now we understand the linear region very well, but we probably still don't understand why would there be a saturation, apart from the fact that, okay, we understand it from the energy band theory that, okay, after you have applied a certain amount of VDS, it does not matter how high the VDS is because it will be limited by the number of electrons present in the source. That's the intuitive understanding of it, that why the saturation region should occur. But you can also prove it mathematically. How we can prove it mathematically? For that, we have to understand this concept a little bit more. And this concept is called the pinch-off. Again, something that we have discussed a little bit in the previous class, but I'd like to repeat it here because this is a very important concept. And without understanding it very well, you'll not be able to solve the problems related to the MOSFETs. So what pinch-off is saying is that as you are applying a drain voltage, so you are applying a VDS. So remember that source is always grounded for an NMOS. So whatever gate voltage you're actually applying a VGS. And whenever you're applying a drain voltage, you're applying VDS. As you are applying a drain to source voltage VDS, remember that this is an N-type region. This is an N-type semiconductor. And the channel region is P-type. So as you are applying more and more drain to source voltage, you're making this PN junction more and more reverse biased. What happens when you have a reverse bias PN junction is that you have a wider and wider depletion region. So what depletion region means is that there will be no majority charge carriers within the depletion region. So as you are applying a higher amount of VDS, the depletion region around the drain will keep on increasing in width, which means that there would be less and less amount of charge carriers, in this case, they are electrons, within the depletion region, because that's the definition of depletion region. You are depleting it of any kind of charge carrier. That's the meaning of a depletion region, that it's depleted of any kind of charge carriers. So if the charge carrier is not present, you'll see less and less number of electrons near to the drain as you're applying more and more drain voltage. So that's one way to understand that why the number of charge carriers will reduce near the drain, because your depletion region is widening. The other way to understand is, again, something that I already told in the beginning of the class, that as you are applying a positive voltage over here, you're attracting the negatively charged electrons in the drain region. So you'll have less amount of negatively charged electron near to the drain. So both of those concepts are true, and both of those concepts tell you the same thing, that the number of charge carriers near the drain will be reduced as you are applying a positive drain voltage. Question? Any voltage creates a depletion region. So you remember the concept of PN junction diode? As soon as you have a negative or you have a reverse bias, you have a depletion. Even without any kind of bias, you have a small depletion region, right? Because of the built-in potential. But we are not drawing the depletion region here in this curve, but it's always there, right? So the depletion region is always there between N and P junction when you are applying a positive voltage. Okay. So depletion region is that the concept of threshold voltage is that you need to cross the depletion barrier, the built-in potential barrier, so that you can expect a current flow through the device. That's the concept of threshold voltage. That you need to reduce the depletion region and reduce it to almost zero, so that you can get a continuous current flow. But the depletion region always exists, and if you apply the reverse bias, the depletion region becomes wider and wider. So What will happen in this case is that as the depletion region is becoming wider, as you are applying more and more drain to source voltage, you'll see something happening like this. So your channel, instead of looking like a rectangle, so let's say your channel look like a rectangle initially, that you have all these negatively charged electrons through the channel. What is now happening is that as you are creating this depletion region around your drain, some of these electrons are not present anymore in the channel. The channel almost looks like a triangle instead of looking like a rectangle, right? So initially it will look like a trapezoid, then it will look like a triangle, then it will start looking like a smaller triangle as you start applying more and more drain to source voltage. So in this right-hand side figure, you are applying a drain to source voltage which is more than the drain to source voltage on the left-hand side. As you have applied more drain to source voltage, you will see this triangle has shifted towards left-hand side. So this point is called the pinch-off point, where you have zero number of charge carriers, or your charge carrier density becomes zero at the pinch-off. This pinch-off point shifts towards left as you're applying more and more drain to source voltage. And this is another way of saying that you have more and more depletion region. So initially the depletion region was small. It was probably very close to the drain. But here the depletion region is larger. So you do not have any kind of charge carrier within this region. And that's the reason why your pinch-off point has shifted towards left. Right? So you can understand it in using multiple different concepts. But this is just one. All right. Now, now what is happening in this case is that from the previous derivations that we did, so let's say we go back to our equation of, let's say 2.7 or 2.9. So if I just clear this up a little bit. So earlier you were taking this integration from x equal to 0 to x equal to L, right? Because that was your channel length when you were in the triode region, that your channel length was L. Now your channel length, effective channel length, is not L anymore. So what is your channel? The channel is basically the region where you have formed enough number of negative charge carriers so that you can call that region effectively an N-channel semiconductor instead of that being a P-channel semiconductor or P-type semiconductor. So since your electrons are only residing within this region and not on the right-hand side where you have depleted it off, the effective length of the channel has reduced in this case. Right? What is the definition of the channel? The definition of the channel is that you are creating a pathway, you are creating a bridge between the source and the drain region by making this part, the part that is below the gate, to be inundated with a large number of electrons. So you are attracting a large number of electrons by applying a positive voltage at the gate, so that you have a bridge between the source region and the drain region. But now what we are saying is that by applying a drain voltage, you are reducing the length of that bridge effectively, that because you do not have the electrons in this region. There are no electrons over here. So by definition, the channel is where your additional electrons existed. Now the length of that channel effectively has reduced. So you can call that L dash or L prime as the effective length of the channel, which you see after you have pinch off. And in that case, if you do the same calculations again, you'll see that you'll end up with this equation, which is half of mu n COX W over L prime times VGS minus VTH whole square. And this document talks about how you can come up with this particular equation from your equation 2.7 and 2.8 to 2.9. So yeah, here instead of x equal to 0 to x equal to L, it will be x equal to 0 to x equal to L prime. And the other thing that will change over here is that your voltage would be from V equal to 0 to V equal to VGS minus VT. So this will be VGS minus VT or VTH. Why is that? Because again, if you look here, the voltage at the source side is VGS minus VT. The voltage at the pinch-off point is 0. Earlier, the pinch-off point was here, that you are integrating from the source to the drain, the entire channel region. And at the drain, the voltage was 0 because this was a voltage that was equal to VGS minus VT. And at your VDS, you are applying some amount of voltage. So those two voltages, so basically what you can probably draw is that so you are applying a VDS at the gate. You have some amount of drop through the gate to channel region. So in the channel, you originally had VGS minus VT. But remember that when you apply a drain voltage, let's say a drain voltage of VDS, the voltage at the channel does not remain constant. That's the first concept we started. The voltage in the channel will be VGS minus VT near the source, but then it will start reducing. Just like you have a triangular channel, you will have a triangular gradient in the voltage that you have. So you had VGS minus VT minus V of X, right? If X is this direction. So that's the voltage in the channel. Now, when you have a pinch off, your voltage becomes 0. Just like the number of electrons or the number of charge carriers are 0 at pinch off, the amount of voltage is also equal to 0. So for this to be equal to 0, how much does your Vx needs to be? Your Vx needs to be equal to VGS minus VT. As your Vx is equal to VGS minus VT, you have pinch off. So that's why when your VDS is equal to VGS minus VT, your pinch off point will be exactly at the drain, at the location of the drain. So as you see over here, your pinch off is happening exactly at the point where your drain is starting, right? And in that case, your VDS will be equal to VGS minus VT. So if your VDS is equal to VGS minus V threshold, then you will have your pinch off point exactly at this point. But if your VDS is more than that, then your pinch off will start shifting towards left. But the point at your pinch off, the point where you have pinch off, that point is still, at that point your voltage will still be equal to 0, which means at that particular X, that X might not be, in this case, the X is equal to L. The X is equal to L, and when your X is equal to L, you have 0 voltage, you have 0 charge density, and you have the pinch off exactly at the location of X equal to L. When you have more VDS, when your VDS increases, your pinch off point will shift towards left. So you'll probably have a triangle that looks like this. So at a particular X, which is less than L, you'll still have VGS minus VT minus Vx equal to 0. So at this particular point, your Vx will still be equal to VGS minus VT. The only difference is that this X is much lower than L now, because your channel has pinched off and you have moved this pinch off point towards left. But the value is still 0. This point, the voltage value is still 0, the charge density is still 0. It's just that it happens even before you reach a channel length of L. And that channel length, the effective channel length is being called L prime in this case. Okay. So if you do that calculation by putting x equal to 0 to x equal to L prime in this integration and v equal to 0 to v equal to VGS minus VTH in this other integration, you'll end up with this particular equation, that ID equal to half of mu and COX times W over L prime times VGS minus VTH whole square. Now you see that there is no dependence on VDS at all, apparently at least, right? There is no VDS term over here in this equation. And that's a reason why that when you have saturation, when your VDS is more than VGS minus VTH, you have the saturation region. Okay, the saturation region is sometimes also called the active region, okay? Because that's the region where you want your transistors to operate because they work as a constant current source in this region. That's the most important property of the MOSFET. So you'd want your MOSFET to operate in this region, because this other region you could have achieved with a resistance as well. You did not need a MOSFET for achieving this linear ID versus VDS characteristic. The MOSFET is only interesting because the MOSFET has the saturation region or the active region. Okay. So in most cases, almost in all cases, when you will be talking about MOSFET devices later on in the course, we'll assume that they are in the saturation region or active region, because that's the most interesting region for the MOSFET for various reasons, and we'll talk about those different applications later on in the class. But the definition of saturation is that your VDS has to be more than VGS minus VT. Okay. All right. So now one interesting thing here is that apparently this does not depend on VDS at all. So you should see an infinite output impedance. Why I'm saying it should have infinite output impedance? What's the definition of output impedance? That you connect a test voltage source at the output, find out how much current is flowing at the input side. So if you connect a test output voltage, an AC output voltage, and in this case, let's just say, and again, as I said earlier in the class, that whenever we are talking about, let's say, output impedance or input impedance, these are AC output impedance, AC input impedance. We're not talking about DC potentials or DC resistances here. It's all AC. Unless you're talking about biasing, we'll come to biasing in the next lecture. But unless you're talking about biasing, it's all AC. So if you're applying an AC voltage at the output, so that means the output voltage is changing by a little bit amount. So your VDS that is moving around, let's say, within a small region, let's say within this point to that point. How much does the current change? The current changes between these 2 points, which are almost same. So what is the ratio of voltage changed over current change? What is the ratio of the change in voltage over the change in current? Ideally infinite, right? Because the change in current is almost zero, even though you have a finite amount of change in voltage. So a finite change in voltage divided by zero change in current means you have an infinite output impedance. That's in the ideal scenario. But as you know that no device actually can give you ideally infinite impedance, right? Infinity does not exist in reality. So it will be a large value, but it will not be infinite. So what's wrong here? What's the catch? So we are saying from the equation that, okay, we do not have any dependence on VDS here. So what's the catch? Why are you still saying that the impedance cannot be infinite? That is because you're using a length which is not the exact physical length. It's L prime, which is the effective length of the channel as the channel has been pinched off. Now, again, we can go into much more detail, but at this point, it suffices to know that this L prime is a function of VDS. And you will probably understand why L prime is a function of VDS is because as you apply more and more VDS, this pinch off point moves towards left, right? So there is a dependence of L prime on VDS. Just from these 2 figures that we had drawn earlier, we had shown earlier that as you are applying a VDS, you have a pinch off, and that pinch off point can move toward left as you are applying more and more VDS. What is definition of your L prime? Your definition of your L prime is this effective channel length, starting from the source to the pinch off point. As we are saying that the pinch off moves towards left while we are applying more and more VDS, which means that L prime is a function of VDS. So even though in this equation, it did not look like that ID is a function of VDS, it is a small function of VDS because ID is a function of L prime and L prime is a function of VDS. Now, the way that dependence or dependency on VDS is represented is, all right, so I'm not talking about here in this document, but the way that dependence on L prime or VDS is usually represented is that you generally write down this equation, and then you have an additional part called 1 plus lambda times VDS. So, and in that case, you'll not talk about L prime, you can talk about just W over L. So half mu COX W over L times VGS minus VT whole squared times 1 plus lambda VDS. That gives you the correct form of the equation that also has the dependency on VDS. So this is another way to represent it if you're not representing with L prime, because you'll probably not know what exactly your L prime is, but depending on the technology, you'll know what would be the value of lambda. So this is usually a constant. The value of lambda is usually in the range of 0.1 or 0.2 or 0.05, within that range. So if you are applying a VDS, additional VDS of 1 volt, this will just become 1, instead of 1, it will become 1.1 because lambda is equal to 0.1. So this is a small change, let's say 10% change in the ID, but that also means that as you are changing your VDS, you'll see a slight increase in your ID. So ID will not be perfectly constant, but there will be a slight increase in ID even in the saturation region. So that's the implication of this additional 1 plus lambda VDS term. So this is what we studied today, and we tried to look into it in more detail, that what is exactly happening in the triode region, what is exactly happening in the saturation region, and this will be very important in solving the homework problems. Now, since we haven't covered exactly how to solve the homework problems, I have extended the deadline till next Wednesday. So in Friday's lecture, we try to look into biasing and how to exactly solve the homework problem so that you get maybe more than half a week to solve the homework 4 problems. And then we'll also talk about AC analysis of the MOSFETs. All right, so we'll stop here. Do you have any questions for today?
So
Yeah.
the active region can be used for voltage amplification.
Yes, voltage amplification, current amplification, all these different things. So we'll talk about the AC analysis of the MOSFET. And then
The triode region is more about like, or could be used for current amplification. Using a volt that trans.
So usually the triode region is used just as a resistance. So you generally don't get an amplification factor over here. You get a voltage amplification in saturation region because your output impedance is infinite, right? Ideally infinite. Your output impedance is infinite. Your output voltage can also be infinite even with a small amount of current. Right? So if you are applying a small amount of voltage at the input, because you have this property that your output impedance is very high, you can get a high amount of output. So you can get voltage amplification in the saturation or active region, but to get current amplification, we generally use the VDS. Yeah, so that's probably the easier way to handle current amplification.
Why would it be bad? Use the MOSFET.
So first of all, MOSFET, you do not have a current going into the gate, right? So if you think about the structure of the
thinking about like if moving DS increases ID in the or decreases ID in the triode region.
That's right. But the input to the, you have to think about, for example, the ID versus VDS characteristic that only comes out the output. But what is the input of the MOSFET? The input of the MOSFET is provided to the gate, and because there cannot be any current flowing into the gate, you know that this is an insulator region, it's metal oxide semiconductor. There cannot be any current flowing into the gate. So the input is, if you are applying it to the gate, it's always a voltage. Okay? So you can get a current at the output, but your input is always a voltage. Unless you apply the current here, let's say in the drain terminal. And in that case, what will happen that the internal current that you are applying in the drain terminal will flow in the source terminal, or like the current that you are applying in the source terminal will flow in the drain terminal. So you have a current amplification of 1, and you cannot get a higher current amplification factor. Right? You cannot create additional current. So that's why MOSFETs are not usually used for current amplification. BJTs are used for current amplification. MOSFETs are used for voltage amplification because you can apply a small voltage here. That will create some amount of current to the device because the current to the device will be GM times VGS. If you apply a gate to source voltage of VGS over here, the current to the device will be GM times VGS. Correct? The transconductance times gate to source. Similar ideas we had used in our amps, right? The GM times VGS is your current multiplied with the output impedance of the device. Now that is called, let's say, R out. Now ideally, your R out is infinite. So GM times VGS is the current multiplied with an infinite output resistance gives infinite voltage. So you get infinite voltage amplification. But of course, R out will not be infinite. R out will show the value of R out, the expected value of R out. In fact, R out will be
region.
1 upon, no, it will be in the saturation, even if it is in the saturation region, it will be 1 upon lambda IT. That will be the value of R out. And we'll prove that in the next class.
Yeah, I mean that when in the lab, like it was like it started like increasing BGS.
Yeah.
And one moment like BGS started to be BGS beyond like BGP. That's what they call it.
So that's a threshold that when your MOSFET turns on as you are
BGS
increasing the
minus
VGS.
BGH.
Yeah.
When it was like less than more than BDS, then it got into the triad region.
Yes.
And there is a thing when the MOSFET starts working.
It will work in a different region. You'll not see any kind of gain anymore because the gain is expected only in the saturation region because your R out is high. If your R out becomes low, which is in the triad region, right? In the triad region, the difference between the saturation and the triad is this, right? In this region, you're infinite. Ideally you have infinite output. Here you have finite, very small output. Now let's look at this equation. You have GM times VGS times R out. If GM times R out is more than 1, then you have a voltage gain. Your input was VGS, your output is this. If GM times R out is more than 1, you have a voltage gain. If it is less than 1, you do not have a voltage gain. In saturation region, you usually have GM times R out to be much more than, it's usually in the range of 20 or 30. So you get a voltage gain of 20 or 30 times. But in triad region, this GM times R out is less than 1, so you do not get any voltage gain.
Like it stays stable.
Yeah, I mean, in that could be a particular case that it was the voltage gain was equal to 1, but it is also possible you get a voltage gain of less than 1, depending on the value of GM and R out. But even in the saturation region, because your R out is high, your GM times R out will be high, so you'll expect a voltage gain. We'll discuss this more in next lecture. But yeah, that's a good point that how you actually get voltage gain using a MOSFET. I think it might be a problem with this as well because I don't. Yeah. Right, so you have more and more BTS. Great question. So how is so you're saying that you now have a depletion region. So there is no so there are electrons over here.
Because it's always represented as if current isn't being
Exactly. So you have the electrons over here. You have electrons in the source region. You have electrons in the drain region, but there is nothing in between. So it's as if the bridge is broken. Right? But the question is how is the current still flowing? Exactly. So how that happens is that we already talked about this, that VDS is much more than zero. It's a positive potential. So it will attract charges. And as it is attracting charges, you have a particular amount of inertia. So let's say you have some charges going from left to right. You have a particular amount of inertia, you have electric field, even though this is a depletion region. Still a fixed amount of charges, depending on how many charges are coming over here. Just because of that inertia, they will go through this depletion region and will be collected at the base. So it's as if that you have a very large voltage here that is creating a large electric field, and that electric field is attracting these electrons from the left side to the right hand side, even though there is no electron in the middle.
So yeah,
it's more like inertia. So it's like you have rolled the ball, and because there is a slope, the ball will eventually reach the previous other side, even though the bridge is broken. So it can, let's say you have a bridge that looks like that, it is broken in the middle, but because of gravity, as it is rolling out, it will not fall through this gap, it will probably go through this, if it has enough energy. So that's what is happening.
and then and if it grows, like it's still saturated.
Yeah.
You can
So
go
even
back
if it grows, so when it grows, what is actually happening is that you have more and more VDS, and that's why the depletion region grows. When you have more and more VDS, the slope of this also increases. So this gap increases, but the slope also increases. So you have more energy, so that that the electron can still pass through this gap and reach the other side. Even though the gap is larger, you have the larger slope, because of which the electron can still reach. So it's a beautiful concept that okay, in one scenario you have something like that, and the other scenario you have something like this. That when the slope is small, the gap is small. When the slope is large, the gap is large. And it turns out in a way that it always equalizes and compensates for each other, and you always have enough amount of energy for the electron to just roll through this slope and reach the other side. Sure. Okay.